welcome again. I am Mohammad Sawaj Alam, Assistant Professor from ABES Engineering College, Department of Electronics and Communication Engineering. In the previous lecture, I have already discussed the common base and common emitter configuration and its VI characteristics. Now, in this lecture, I am going to discuss the common collector configuration and DC load line and operating point. First of all, I am going to discuss the common collector configuration. This is the circuit diagram for common collector configuration. Since this is common collector configuration, so that the collector is grounded and the input terminal is the base terminal and output terminal is the emitter terminal. This configuration is also known as emitter follower configuration. Why it is called emitter follower configuration? Because the output is taken from the emitter terminal. This means the output voltage follows the emitter voltage, that is why it is also known as emitter follower configuration. Now, to draw the IV characteristics, we have taken 4 meters, 2 ampere meters and 2 volt meter. And since this ampere meter will measure the base current, so that the order of this ampere meter is in microampere. On the other hand, this ampere meter will measure the emitter current, the order of this ampere meter is in order of milliampere. Okay, guys. Now, there are 2 voltmeter. 1 voltmeter will measure the output voltage, that is the emitter voltage with respect to ground. This means that will measure the VEC. On the other hand, this voltmeter will measure the input voltage with respect to ground. This means this will measure the VBC here. Now, since output terminal is the emitter terminal and input terminal is the base terminal and collector terminal is taken as common with respect to input and output, so that now I have to define the current gain of common collector configuration. Now, the current gain of common collector configuration is denoted by gamma, and it is defined as the output current upon input current, that is IE upon IB. Now, IE can be written as like this. IE can be written as IC upon plus IB upon IB. Now, this will equal to the IC upon IB plus 1. Now, IC upon IB is taken as beta and plus 1. This means gamma is equal to the 1 plus beta. Gamma is equal to 1 plus beta. All of us know that the value of beta is in between 50 to 350. This means the value of gamma is greater than that of beta. This means gamma is greater than beta. Now, we can also write the value of gamma in terms of alpha, and this is equal to, now beta can be written as 1 plus beta. This means, and beta is written as alpha upon 1 minus alpha. This means this is equal to 1 upon 1 minus alpha. This means the relation between alpha 1 plus beta, this means this is equal to gamma. Gamma is equal to 1 plus beta and this is equal to 1 upon 1 minus gamma. This means the relation between gamma and alpha is like this, and the relation between alpha and beta is equal to alpha upon 1 minus alpha. So, this means we can write the all types of relation, the relation between alpha and beta, the relation between beta and gamma, and the relation between gamma and alpha. Alpha is equal to beta upon 1 plus beta, and beta is equal to alpha upon 1 minus alpha, and gamma is equal to 1 plus beta, and gamma is also equal to 1 upon 1 minus gamma. So, these are the relation. Whenever you will solve the numericals, you can use these relations. Now, input and output characteristics of common collector configuration. Since we have designed an experimental circuit in the very first slide, you can see that here. Now, to draw the input characteristics, what we should have, what we should do, that that we have to kept the output terminal, this means output voltage constant, that this means the VEC should be remains constant, and after keeping this constant we have to change the input voltage and note down the readings of this microampere meter and this voltmeter in small intervals, and we will have an observation table. Then we will draw the graph. In x axis we have taken the voltage VBC, this means voltage of input terminal with respect to ground, since collector is ground here, and in y axis we have taken the input current in order of microampere. Now, we will see here that when the input voltage will increase, this means the input current will decrease like this. You can see that I think the change in voltage upon change in current will be here negative parameter. Why it is negative parameter? If we will take 2 points here, then what will be here? Change in voltage will be the negative and change in current will be the positive. This means here is a negative resistance, we can say that. Why it is like that? If we increase the base voltage, the current decreases, or we can say if we will decrease the base voltage, the current will increase. Why like this? Why it is like that? It is like that because we can see that in the common collector configuration here, this is the common collector configuration, this is the collector terminal and collector terminal is grounded here, and this is the emitter terminal and this is the base terminal. This means when we will increase the base voltage increase means VBC increase, then what will be here? What will be here? That the reverse voltage here, the depletion layer between the collector and the base layer will increase. This means that due to increase in the depletion layer, the number of holes or number of majority carrier at the base layer will decrease. This means the recombination current will decrease. This means the base current will decrease. So, this is the reason that why if we increase the VBC, then the current decreases here. Now, this is the output characteristics of common collector configuration. Here when we will draw the output characteristics, this means output characteristic will be drawn between the VCE, VCE versus IE. Why I have written here VCE? Because VCE is positive. We will see the first slide, then we can understand that why I have taken VCE. Why VCE here? Because the collector, the emitter terminal is connected with the negative plate of the battery. This means the VEC will be negative. This means we have to draw it, we have to take it in the negative x axis, but we have taken in the positive x axis, that is why we have taken VCE here. Now, y axis is the emitter current. Now, we have to take care that when we will draw the output characteristics, we have to take the input current constant. Why input current must be constant? Because BJT is the current controlled device. BJT is the current controlled device. This means that IE is the function of base current, so that there should not be the effect of base current on the output characteristics. So that we have to taken the input current, that is base current, taken as a constant. Now, when we will take the observation table at constant base current, then we will like this, we will have this graph also. Now, there are also 3 types of region. At the left side, this is the saturation region and this is the active region, and now when IB is equal to 0, then below the IB is equal to 0, this region is called the cutoff region. Now, we can easily calculate the output resistance also when we will take 2 points here, and then we will have the change in voltage and change in current. By taking the ratio of change in voltage upon change in current, we will have the output impedance of the common collector configuration. Now, one question arises that how many configuration of BJT are there and which one of them is not used as an amplifier. The answer is that common collector configuration is not used as an amplifier. Why it is? Because the current gain is highest, but the voltage gain of common collector configuration is near to unity. Since voltage gain is near to unity, so that we cannot use this configuration as an amplifier, because for amplification what is the condition? The voltage gain should be greater than 1. Since the voltage gain is near to unity, so that it is this configuration cannot be used as an amplifier, this configuration can be used as an impedance matching. So that only two configurations are used as an voltage amplifier, or you can say amplification purposes. Only common collector, common base and common emitter configuration are used as an amplifier. And amongst the common base and common emitter configuration is superior than that of common base, because there are many reasons that we prefer the common emitter configuration as an amplifier. The first reason is that the current gain for common emitter configuration, that is beta, is greater than alpha, and the most important feature of common emitter configuration is that the power gain of common emitter configuration is greater than that of common base configuration. And one more important feature is that the input impedance of common emitter configuration is greater than that of common base configuration. These are the reasons that due to which we prefer the common emitter configuration as an amplifier. Now, another topic, very important topic, is the DC load line and operating point or quiescent point or silent point. Now, first of all we will discuss the DC load line. Now, this is the simple circuit diagram of a common emitter configuration. Here this is the VCC, this is the VBB, two voltage method. Now, when we will write the KVL equation at the output loop, what will we get? Now, I want to write a KVL equation in the output loop. Output loop means through the collector. Now, what will here? We will write the KVL equation, start from here. Then what will we get? We get VCC minus ICRC. Now, we have here, now this is emitter, this means minus VCE, this is equal to 0. Now, what we will have the value of IC. Now, what will be the value of IC here? The value of IC will be the VCC upon RC minus 1 upon RC into VCE. This means we will have this equation is that this is the constant. This is the constant because VCC is also constant and RC is also constant, but this is variable and IC is variable. This means IC depends on VCE and minus 1 upon RC is the slope. Then this equation is like a equation of straight line equation, like a straight line equation where VCC upon RC is the constant and this is the slope, this means m, and this is the x, that is y is equal to mx plus c. Now, this is treated as a y and this is constant and this is slope and this is x. This means this equation is nothing, this is the equation of straight line. We can say that this is the equation of straight line mx plus c. This means m means minus 1 upon RC VCE plus VCC upon RC. This is the IC. This is the very important equation, that is straight line equation, ST line equation. Now, we have to draw this equation. Then we have to find, we can draw any straight line by taking 2 points only, by calculating the coordinates of 2 points only. Now, we can easily calculate the coordinates of 2 points. When IC is equal to 0, where IC is equal to 0, now this is VCE and this is IC. At x axis the value of IC is equal to 0. When IC is equal to 0, then what will be the value of VCE? The value of VCE is equal to VCC here. This coordinate is nothing. This is the VCC comma 0. We can easily calculate this value. And now, at x axis the value of VCE is equal to 0, then what will be the value of IC? here the value is 0 comma VCC upon RC. These are the two values. Now we can easily draw this straight line. This is called the DC load line. This is called the DC load line. I can draw it here on this graph also, because we have taken the value of VCC is 12 volt. We can easily see in the circuit that we have taken the value of VCC is equal to 12 volt. This means the coordinates are here coordinates are 12 volt, here 12 volt, and current is here 0. The coordinates are this, P is equal to 0 comma 12 and here R is equal to 12 comma 0. These are the coordinates, and R is equal to, what is the value of R? We can see here in the circuit. What is the value of RC? The value of RC is 1 kilo ohm. Okay, guys. So that the coordinate of this straight line PR is the 0 comma 12 and here 12 comma 0. These are the coordinates. This is called the DC load line. Why it is called DC load line? Because this is the straight line of DC current, DC output current, this means DC load current. Since this is the straight line of DC load current, that is why this is called DC load line. Okay, guys. Now we can see that PR straight line PR is the DC load line. If anyone will ask you that define DC load line, how you will define the DC load line? Simply the line of DC load current is called DC load line. Now these are the methods to calculate the coordinates. Already I have discussed this point. Now already discussed this point, okay, guys, to calculate the DC load line. Now DC load line slope, changing the collector supply voltage while keeping the same collector resistance produces two load lines. What does mean this? अगर हम लोग कलेक्टर सप्लाई वोल्टेज VCC को क्या रखें, while keep VCC को चेंज करें और कलेक्टर रेजिस्टेंस RC को अगर हम लोग कांस्टेंट रखें तो हमें दो पैरेलल DC लोड लाइन मिलेंगे, like this in the next slide here. Suppose this is also the DC load line, this is also the DC load line, just we have changed the VCC, means collector supply voltage, but the condition is that the resistance should be constant. Resistance should be constant. Why it is like that? Because we know that the value of this value IC here is equal to VCC upon RC, and here the coordinate is VCC comma 0 and here 0 comma VCC. Then what will happen that if we will change the VCC by keeping the RC constant, then what will, if we change the VCC, then it will shift like here. सपोज हम लोग 12 वोल्ट से 16 वोल्ट ले लिया VCC, तो अब ये पॉइंट यहाँ पे आ गया और ये पॉइंट 16 पे यहाँ पे आ जाएगा. ठीक है गाइस, तो इसीलिए DC लोड लाइन क्या होगा, जस्ट इसके पैरेलल होगा. लेकिन इसका एक उल्टा है कि अगर हम VCC कांस्टेंट रखें और RC को चेंज करें तब क्या होगा, तब आप देख सकते हैं कि वो चीज़ें चेंज हो जाएगी. अगर हम क्या किए, VCC कांस्टेंट रख दिया और RC को चेंज करेंगे तो ये आपको ग्राफ मिलेगा, क्योंकि VCC हमने कांस्टेंट रखा, RC किसको इफेक्ट करेगा, इस वाले करंट को, क्योंकि VCC अपॉन RC हमने RC चेंज किया, इसीलिए यहाँ पे जो है ये कोऑर्डिनेट यानी IC की वैल्यू चेंज करेगा. तो इस तरह से आपको दो अलग अलग ग्राफ्स मिलेंगे. अब ये दोनों DC लोड लाइन ये पैरेलल नहीं हो सकता. तो कीपिंग दिस पॉइंट इन योर माइंड दैट इन व्हिच केस द टू लोड लाइन्स, टू DC लोड लाइन्स ऑफ एनी ट्रांजिस्टर इज पैरेलल, द कंडीशन इज दैट द VCC should be variable but RC should be constant. Okay guys. Now we are going to discuss the operating point. Operating point some people called is the quiescent point. Quiescent is the Latin word and the meaning of quiescent is silent. This means the feature, the characteristics of the operating point or quiescent point should be silent. This means should be static. When the operating point will static, we will discuss it in later. First of all, we have to define the operating point or quiescent point. Now, I am going to discuss the operating point by some examples here. Suppose this is the graph. This is the graph. The operating point is called Q point or quiescent point. This is the graph. We have taken 3 points in the DC load line. Suppose this is the DC load line AB. Now, I have taken 3 points. One point is the P, another point is the Q, and third point, suppose third point is at the, suppose I have taken R, P, Q, R. Now, there are 3 points. P is near the saturation region, on the other hand R is near the cutoff region, on the other hand Q is just at the mid of the DC load line. Then what will happen here? If there will be slightly variations in collector current or collector voltage, what will happen here? The P point and R point may shift into the cutoff region or saturation region, and all of us know that the transistor will amplify signal, or transistor is used as an amplifier only in the region of active region. So that guys, we can take care of that. We have taken 3 points P, Q and R. P is near the saturation region and R is near the cutoff region. What will happen here? If there will be slightly increase in the collector current, अगर यहाँ पे थोड़ा सा भी किसी भी कारण से, किसी भी वजह से, रीजन से अगर कलेक्टर करंट इंक्रीज होगा तो ये पी पॉइंट कहाँ पे शिफ्ट कर जाएगा? सैचुरेशन रीजन में, और सैचुरेशन रीजन में ट्रांजिस्टर एम्पलीफायर की तरह यूज नहीं होता और आपको कुछ ना कुछ डिस्टोर्शन आपको मिलेगा। क्या मिलेगा? वहाँ पे आउटपुट सिग्नल में डिस्टोर्शन मिलेगा, और वो लीनियर बिहेवियर जो होता है एक्टिव रीजन में, वो आपको लीनियर बिहेवियर आउटपुट सिग्नल का नहीं मिलेगा, लीनियर एम्प्लीफिकेशन आपका नहीं होगा। ऑन द अदर हैंड आर पॉइंट के बारे में क्या है कि अगर थोड़ा सा भी कलेक्टर करंट डिक्रीज हुआ, थोड़ा सा भी डिक्रीज हुआ तो ये पॉइंट कहां पे चला जाएगा? कट ऑफ रीजन में चला जाएगा, एंड वी विल नॉट यूज एज एन एम्पलीफायर। कट ऑफ रीजन में जाने की वजह से आपको आउटपुट सिग्नल में अगेन डिस्टॉर्शन होगा। ऑन द अदर हैंड Q point is just at the mid of the DC load line. Slightly variations in collector current or collector voltage cannot shift this point into the cutoff or saturation region, so that Q point is taken as operating point. This means the values of Q point is taken as the collector voltage and collector current to operate the transistor in active region and as an amplifier. That is why Q point is called operating point. क्यों कहते हैं operating point? Operating point यानी ट्रांजिस्टर को इसी वैल्यूज पे, यहाँ पे वैल्यूज क्या होगा? VCE, IC, जो भी इसकी वैल्यू होगी, इसी वैल्यूज पे ट्रांजिस्टर को हम लोग ऑपरेट करेंगे। किस तरह से ऑपरेट करेंगे? एज एन एम्पलीफायर। इसीलिए इसको हम लोग ऑपरेटिंग पॉइंट या क्विसेंट पॉइंट या साइलेंट पॉइंट कहते हैं। शॉर्टकट में इसे हम लोग क्यू पॉइंट से रिप्रेजेंट करते हैं। तो दिस इज द सिलेक्शन ऑफ ऑपरेटिंग पॉइंट गाइस। नाउ quiescent point, the behavior of quiescent point should be silent, but there are various factors that Q point is compelled to shift into the cutoff and saturation region, so that we have to discuss the factors affecting the quiescent point, because all of us know that the collector current is the function of base current, that this means beta IB plus 1 plus beta ICBO. This means the collector current is the function of base current as well as the beta value depends, beta also, IC also depends on beta, and IC also depends on leakage current. So we should know the dependency of collector current on various parameters, then only we can keep the quiescent point constant at the mid of the DC load line. So that In the next lecture, we will discuss the factors affecting the Q point, and then after we will discuss that how should we can stabilize the Q point at the mid of the DC load line, and that is called the bias stabilization. So that guys, you can easily solve these questions, various types of DC analysis, and thank you. And the references are taken from Robert L. Boylsted and Albert Malvino. There are 2 good books. And now, okay guys, thank you. We will meet in the next lecture soon.